Hello there and welcome to Lower 6th Further Maths A-Level. This is the revision video 4 for the January mock exam. Here we're working on question 1. So question 1 says that given that a equals 4, so let's substitute that in straight away, find the modulus of z, so 2 plus 8i, so 2 plus 4i because it's now 4. Okay, so what I'm going to do here is we'll find the modulus of this complex number here and here. Now what I'm going to do is I'm going to bring in one of those rules to do with moduluses of complex numbers, where if I divide one complex number by another and find the modulus of it, another way of working out that modulus is just to divide the two moduluses separately. So this is a rule here you can bring in at any point in time in your exam. And that's what I'm going to do with this question here. I'm going to work out the modulus of 3 plus 4, so 4 plus 3i, separately from the modulus of 2 plus 4i. And then I'm going to divide one by the other. So just a reminder then, the modulus of a complex number is its distance on an arcane diagram from the centre to its coordinate, effectively 4 plus 3i in this case here. Now we can all see here that we've formed a right angled triangle here, so this is going to make just a simple distance on a Pythagoras triangle. So it's going to be 4 squared add 3 squared. Now we don't need to include the I here because it's just a distance up on the I-axis of 3. So it's just 4 squared plus 3 squared. And then this is going to be the square root of 2 squared plus 4 squared. And now we just need to work these out. So the top one here, that's going to be a 5. And the bottom one here, that's going to be a square root of 20. And this will simplify to 5 over 2 root 5. Cancel out root 5s and you get 5 over root 5 over 2. Okay, so what we can do now is check this on our calculator. So if you go to the menu button on your calculator, hit option number 2 and then type in your complex number using the fraction button. To select I, you need this eng button in the middle of your calculator just above the 8. See the purple I just above it? That's the I that you need to use. And then once you've typed in that complex number, hit the options button, scroll down once, hit option number 1, and that will convert your complex number into modulus argument form. You see the r and the theta there, that's the radius and the arguments effectively there. So hit enter on that and you get exactly what you want. R is your root 5 over 2 and your argument is this minus 0.46 etc etc. Okay, so that's how you can check your answer on the calculator. Alright, part B then. So we have z equals a plus 3i and 2 plus 3i, but this time we're finding the modulus, sorry, we're finding the argument of the complex number, and it has to equal pi by 4. Okay, so what we're going to have to do here, unfortunately, is when we work out the argument of the complex number, it's always tan minus 1 of the imaginary part over the real part, and then we have to do some small adjustments depending on which quadrant it's in. Okay, so what we'll have to do then is rationalize this denominator. So we're going to now times the top and bottom by the complex conjugate of the denominator, so 2 minus ai and 2 minus ai, and we're going to simplify this. So it's going to be 2a, think about this as times in fractions together. It's a double bracket on the top, so we need to times everything from the left hand bracket by everything in the right hand bracket. So 2, then it'll be minus a squared I, and then the next bit's going to be plus 6i, and then the next bit's going to be minus 3ai squared. We'll simplify that I squared in a little bit. And then on the bottom here we've got two fractions as well, sorry, two brackets as well, so it's going to be 4 plus 2ai minus 2ai, and then it's going to be minus a squared I squared. Now hopefully everything from the denominator there has become real, so we're going to get 4, and then I squared here, remember that I squared will get simplified to a minus 1, so this is going to be minus a squared times minus 1, so that would be plus a squared. And the same will happen to this minus 3a I squared here. That will become a plus 3a. So in total we'll get 5a on the numerator, and we're going to get plus bracket 6 minus a squared on the I there. Alright. So what we're going to do with this now is, if the argument of our complex number is pi by 4, then on the argand diagram it's going to appear on this line here, so pi by 4 here. And pi by 4 is exactly half over a right angle pi by 2. So it's going to lie exactly on the line of effectively y equals x, or the real part equaling the imaginary part. So that's what I'm going to set up in this complex number here. I'm going to set the real part of this complex number, which is 5a over 4 plus a squared, equal to 6 minus a squared over 4 plus a squared. I don't need the I here because this is my imaginary part, just not times by the I. Right, now I need to solve this equation. I can get rid of the denominators because I can just times through by 4 plus a squared, and that will always be greater than 0. And now I've just got a quadratic here now, so I'm going to get a squared plus 5a minus 6 equals 0. And from this I can solve the quadratic equation by putting it into two brackets. So I think I'm going to get a plus 6 and a minus 1. So therefore a is minus 6 or a is 1. Now we can't stop here, because even though we've used the assumption that the real part will equal the imaginary part, it definitely has to have a argument of pi by 4, meaning that my solution could have appeared down in this section here. So I just need to make sure that one of my solutions hasn't done that, and it has to appear in the top section here. So I'll plug both of my solutions back in to Z and see where I end up. So, or actually I won't plug it into Z, I think I'll plug it into this version of Z here. That would probably be a bit better. So when Z equals minus 6, so A equals minus 6, sorry, I'm going to get minus 30, and then this is going to be 6 squared is 36, 6 take away 36 is 30, so it's going to be minus 30i over something. So that is not going to be a solution here, because it's definitely down in this bottom left hand quadrant here on minus 30, and then divided by some fraction. When a equals 1, I'm going to get 5 plus 5i over 5. So I'm going to get 1 plus 1i. Okay, so show that there is only one value of a for which this is true, and that value of a, everyone, is the value 1. Alright, so quite tricky that one, first one in this revision sheet. Hopefully it gets easier as we go along. 6 marks.